Imagine light racing through the vast emptiness of space, illuminating distant stars and galaxies in its path. This light travels at an incredible speed of 299,792,000 kilometers per second through the vacuum of space. For over a century, scientists have believed this speed to be the ultimate cosmic speed limit, the fastest anything can travel in our universe. But what if this fundamental rule could be broken? What if particles existed that could travel even faster than light itself, defying the very laws that govern our understanding of reality? Tonight, we embark on a journey to explore one of the most intriguing concepts in theoretical physics, particles called tachyons. These mysterious hypothetical particles are theorized to always travel faster than light, challenging everything we thought we knew about space, time, and the fabric of the universe itself. The very idea of tachyons forces us to question the boundaries of what we consider possible. If tachyons truly exist, they would represent a fundamental shift in our understanding of physics. They could potentially allow for effects that seem impossible, like traveling backward through time, or communicating instantaneously across vast distances. The implications are staggering and mind-bending. As we gaze up at the night sky, we see light that has traveled for millions or even billions of years to reach us. This light carries information about the past, about distant worlds and cosmic events that occurred long before our planet even existed. But what if there were particles racing through space right now, carrying information faster than light itself? The concept of tachyons emerged from the mathematical equations of relativity and quantum field theory, not from direct observation. These equations, which describe the fundamental nature of space and time, seem to allow for the possibility of particles that exist in a realm beyond our everyday experience. Tonight, we will explore whether tachyons could really exist, what their properties might be, and how they could revolutionize our understanding of the cosmos. We will delve into the theoretical foundations that predict their existence, examine the challenges they pose to our current understanding of physics, and consider what their discovery might mean for the future of science and exploration. The speed of light has stood as an unbreakable barrier for over a century, but the possibility of tachyons suggests that this barrier might not be as absolute as we once believed. Could these faster-than-light particles be the key to unlocking new dimensions of reality? As we begin this exploration, we invite you to open your mind to possibilities that might seem impossible, to consider concepts that challenge our most basic assumptions about the nature of existence itself. The universe is full of mysteries waiting to be uncovered, and tachyons represent one of the most fascinating puzzles in modern physics. Join us as we venture into the realm of the theoretical, where mathematics meets imagination, and where the impossible might just be waiting to be discovered. The journey begins now, as we seek to answer the question that has captivated physicists for decades. Do tachyons really travel faster than light? The speed of light stands as one of the most fundamental constants in our universe, a cosmic speed limit that has shaped our understanding of reality for over a century. At exactly 299,792,458 meters per second in a vacuum, light travels at a pace so incredible that it can circle the Earth more than 7 times in just 1 second. To truly appreciate this staggering speed, imagine a photon of light leaving the sun. It races through the vacuum of space, covering the 93 million mile distance to Earth in just 8 minutes and 20 seconds. This same photon could travel from New York to Los Angeles in just 16 thousandths of a second, far faster than the blink of an eye. This remarkable speed was first measured with precision in the late 1600s by Danish astronomer Ole Rømer, who studied the eclipses of Jupiter's moons. However, it wasn't until Albert Einstein's groundbreaking work in 1905 that we truly understood its profound significance. Einstein's theory of special relativity revealed that the speed of light is not just fast, It is the absolute speed limit of the universe itself. The journey to understanding light's true nature took centuries of careful observation and brilliant insight. In the 1600s, scientists debated whether light was a wave or a stream of particles. Isaac Newton favored the particle theory, while Christian Huygens championed the wave theory. It wasn't until the early 1800s that experiments by Thomas Young seemed to settle the debate in favor of waves. But the story became more complex in the late 1800s when James Clerk Maxwell developed his equations describing electromagnetic radiation. These equations predicted that light was an electromagnetic wave, traveling through space at a specific speed determined by fundamental constants of nature. Maxwell's equations also suggested that this speed was the same for all electromagnetic radiation, from radio waves to gamma rays. According to Einstein's equations, as any object with mass approaches the speed of light, something extraordinary happens. The energy required to accelerate it further increases dramatically, approaching infinity as the object nears light speed. This means that nothing with mass can ever reach or exceed the speed of light, no matter how much energy is applied. This cosmic speed limit has profound implications for our understanding of space and time. Einstein showed us that space and time are not separate entities, but are woven together into a single fabric called space-time. The speed of light determines how this fabric behaves, dictating how objects move through space and how time flows for different observers. The constancy of light speed led to one of the most revolutionary insights in physics. Unlike the speed of a car or a baseball, which depends on the motion of the observer, the speed of light is the same for everyone, regardless of how fast they are moving. This seemingly simple statement has profound consequences that challenge our everyday intuitions about space and time. When we look up at the night sky, we are literally looking back in time. The light from the nearest star beyond our sun, Proxima Centauri, takes over 4 years to reach us. The light from the Andromeda Galaxy, our nearest galactic neighbor, has traveled for over 2 million years. The light from the most distant galaxies we can observe has traveled for nearly 14 billion years, carrying information about the universe as it existed when it was young. This cosmic speed limit means that information cannot travel faster than light, creating a fundamental barrier to instantaneous communication across vast distances. If an alien civilization existed around Proxima Centauri and sent us a radio message today, we would not receive it for over 4 years. Our reply would take another 4 years to reach them, making real-time conversation impossible across interstellar distances. The constancy of light speed also gives rise to some of the most mind-bending effects in physics. Time dilation occurs when objects move at high speeds relative to each other. For a traveler moving at 99% the speed of light, time would pass much more slowly compared to someone at rest. What seems like a year to the traveler might be decades to the stationary observer. This effect has been measured with atomic clocks on high-speed aircraft and confirmed countless times. GPS satellites must account for time dilation effects to maintain their precision. Without these corrections, GPS systems would accumulate errors of several miles per day. Length contraction is another consequence of approaching light speed. Objects appear to shrink in the direction of their motion as they approach the speed of light. These effects are not illusions, but represent the actual nature of space-time itself. A spacecraft traveling at 99% light speed would appear to be compressed to just 14% of its original length to a stationary observer. The speed of light also plays a crucial role in the famous equation E equals mc squared, which reveals the equivalence of mass and energy. This equation tells us that even a tiny amount of mass contains an enormous amount of energy, and it explains how stars shine and how nuclear reactions release such tremendous power. In our everyday experience, nothing approaches the speed of light. The fastest spacecraft humans have built, the Parker Solar Probe, travels at speeds of about 160 kilometers per second, which is less than 1/20th of 1% the speed of light. Even the most energetic particles in cosmic rays, accelerated by the most powerful forces in the universe, can only approach but never reach the speed of light. The speed of light governs the behavior of matter and energy throughout the universe. It determines how quickly information can spread, how fast energy can be transported, and how rapidly changes can propagate through space. This fundamental limit shapes everything from the structure of atoms to the evolution of galaxies. In particle accelerators, scientists routinely accelerate particles to speeds approaching the speed of light. As these particles gain energy, they also gain mass, requiring ever more energy to accelerate them further. No matter how much energy is applied, particles with mass can never quite reach light speed, always falling just short of this cosmic barrier. This universal speed limit has stood as an unbreakable law of physics for over a century. It forms the foundation of our understanding of the cosmos, from the smallest subatomic particles to the largest structures in the universe. The speed of light determines how stars form, how galaxies evolve, and how the universe itself expands. Yet despite its fundamental importance, the speed of light raises profound questions. Why does this particular speed serve as the cosmic speed limit? What would happen if particles could somehow exceed this barrier? These questions have led physicists to explore the theoretical possibility of particles that might exist beyond this limit. The mathematical equations that describe the behavior of particles and fields in our universe are remarkably precise. They have predicted the existence of particles and phenomena that were later discovered through experiment. These same equations, when explored in their most general form, seem to allow for solutions that describe particles moving faster than light. This is where the story of tachyons begins. These hypothetical particles emerge not from experimental observation, but from the mathematical structures that govern our universe. They represent a theoretical possibility that challenges our most basic assumptions about the nature of reality. The speed of light has been measured and verified countless times with incredible precision. Modern measurements using laser interferometry can determine the speed of light to within a few parts in 10 to the 14th power. It serves as the foundation for technologies we use every day, from GPS satellites to fiber optic communications. Yet the possibility that particles might exist beyond this cosmic speed limit continues to intrigue physicists and challenge our understanding of the fundamental laws of nature. Could there be a realm of physics that exists beyond the speed of light, populated by particles that have never been observed, but might nevertheless be real? The implications of the speed of light extend far beyond physics textbooks into the very fabric of our reality. Consider the light from a distant star that began its journey millions of years ago. When that light finally reaches your eyes tonight, you are seeing that star not as it is now, but as it was in the ancient past. The star itself might have long since died, yet its light continues to race across the universe, carrying the image of its former glory. This cosmic time delay affects everything we observe beyond our immediate vicinity. When astronomers study distant galaxies, they are essentially looking at a cosmic museum, filled with images from different eras of the universe's history. The farther we look, the further back in time we see. The cosmic microwave background radiation, which fills all of space, carries information from when the universe was only 380,000 years old. The speed of light also determines the structure of causality itself. Events can only influence other events if they are connected by signals that travel at or below the speed of light. This creates what physicists call light cones, regions of space-time that can be causally connected. Events outside these light cones cannot influence each other, creating a fundamental ordering of cause and effect throughout the universe. This causal structure has profound implications for how information spreads through space. If a massive star explodes as a supernova, the light from that explosion spreads outward at the speed of light, creating an expanding sphere of information about the event. Inside this sphere, observers can know about the explosion. Outside it, the event has not yet happened from their perspective. The speed of light also governs the behavior of electromagnetic fields themselves. When you move a magnet, the changes in the magnetic field propagate outward at the speed of light. Radio waves, which are just another form of electromagnetic radiation, travel at this same cosmic speed limit. This is why there is a noticeable delay when communicating with spacecraft near other planets. In the realm of quantum mechanics, the speed of light plays an equally fundamental role. The uncertainty principle, which describes the inherent fuzziness of quantum particles, is intimately connected to the speed of light and other fundamental constants. Virtual particles, which pop in and out of existence in the quantum vacuum, must obey relativistic constraints that depend on the speed of light. The speed of light also appears in the equations that describe how space itself can expand. In Einstein's general theory of relativity, the geometry of space-time is determined by the distribution of matter and energy. The speed of light appears in these equations as a fundamental parameter that determines how strongly matter curves space-time. During the early moments of the universe, inflation theory suggests that space itself expanded faster than the speed of light. This does not violate relativity because it is space itself that is expanding, not objects moving through space. This rapid expansion explains why the universe appears so uniform in all directions, despite the fact that light has not had time to travel between distant regions. The speed of light also sets limits on how quickly information can be processed and transmitted. In our modern world of computers and communication networks, signals can travel no faster than light through optical fibers or wireless transmission. This fundamental limit affects everything from internet latency to the design of supercomputers. Even the forces that hold atoms together respect the speed of light limit. The electromagnetic force, which binds electrons to nuclei, propagates at the speed of light. If the charge of an electron were to suddenly change, the effects would ripple outward at light speed, affecting the surrounding electromagnetic field in an expanding sphere. The strong nuclear force, which holds protons and neutrons together in atomic nuclei, also has a finite speed of propagation. While this force is much stronger than electromagnetism, it cannot transmit information faster than light. The same is true for the weak nuclear force, which governs certain types of radioactive decay. These fundamental limits shape the very structure of matter itself. The size of atoms, the stability of nuclei, and the properties of chemical bonds all depend on the speed of light appearing in the equations of quantum mechanics and relativity. Without this cosmic speed limit, atoms as we know them could not exist. The speed of light also determines the rate at which stars can burn their nuclear fuel. In stellar cores, the energy produced by nuclear fusion must diffuse outward through the star's interior. This process is limited by the speed of light, affecting how quickly stars can shine and how long they can sustain themselves. In black holes, the speed of light plays a crucial role in defining the event horizon, the boundary beyond which nothing can escape. The event horizon is located at the distance where the escape velocity equals the speed of light. Inside this boundary, space-time itself is so severely curved that all paths lead toward the center, making escape impossible. The speed of light even affects the ultimate fate of the universe. As the universe expands and galaxies move apart, they will eventually recede from each other faster than light can travel between them. This does not violate relativity, as it is the expansion of space itself that carries them apart. Eventually, each galaxy will be surrounded by an observable universe that contains fewer and fewer neighbors. Throughout all of these phenomena, the speed of light serves as the fundamental constant that connects space and time, matter and energy, cause and effect. It is woven into the very fabric of reality, determining how the universe behaves on every scale, from the smallest subatomic particles to the largest cosmic structures. Yet, despite its fundamental importance, and the countless experiments that have confirmed its constancy, the speed of light raises deep questions about the nature of reality. Why does this particular speed serve as the ultimate limit? What would a universe look like if this speed were different? And most intriguingly, what if there are aspects of reality that exist beyond this cosmic speed limit? These questions have led physicists to explore the boundaries of our understanding, to probe the mathematical structures that underlie our physical theories. In doing so, they have discovered that the equations of physics, when pushed to their limits, seem to allow for possibilities that challenge our most basic assumptions about the nature of space, time, and causality. The speed of light has been humanity's cosmic speed limit for over a century, but the universe may hold surprises that extend beyond even this fundamental boundary. As we continue our exploration of the cosmos, we must remain open to the possibility that reality is stranger and more wonderful than we can currently imagine. As we contemplate the vast cosmos above us, we are reminded that the light carrying these images to our eyes represents the fastest information can travel according to our current understanding. But what if this understanding is incomplete? What if the universe holds secrets that exist beyond even the speed of light itself? In the quiet halls of theoretical physics, where equations dance on blackboards and mathematics probes the deepest mysteries of existence, a remarkable possibility emerged in the middle of the 20th century. Scientists discovered that the very equations describing the fundamental nature of reality seemed to allow for something extraordinary: particles that could travel faster than light itself. These hypothetical particles were given a name that captures their remarkable property: tachyons, from the Greek word tachys, meaning swift or fast. The story of tachyons begins not with experimental discovery, but with mathematical exploration. In 1962, physicists Gerald Feinberg, Oleksa Belaniuk, and Vijay Deshpande independently began investigating what would happen if particles could exist that always traveled faster than the speed of light. Unlike ordinary particles, which can never reach light speed, these theoretical particles would be forever trapped above the cosmic speed limit, unable to slow down to light speed just as normal particles cannot speed up to it. The mathematical foundation for tachyons emerges from Einstein's famous equation relating energy, momentum, and mass. For ordinary particles, this equation requires that the mass be a positive real number. But when physicists extended this equation to consider particles moving faster than light, something strange happened. The mathematics seemed to require that these faster-than-light particles have what is called imaginary mass. This does not mean that tachyons are imaginary in the sense of being unreal. Rather, imaginary mass is a mathematical concept where the mass is multiplied by the square root of -1, a mathematical entity that allows physicists to describe phenomena that cannot be represented by ordinary real numbers. This imaginary mass gives tachyons their unique properties and distinguishes them fundamentally from all the particles we know and observe. One of the most remarkable features of tachyons is that they would experience time and energy in ways completely opposite to our everyday experience. For ordinary particles, adding energy makes them move faster and increases their mass. For tachyons, the reverse would be true. As a tachyon gains energy, it would actually slow down, though it would still be moving faster than light. Conversely, as a tachyon loses energy, it would speed up, potentially reaching infinite velocity as its energy approaches zero. This bizarre relationship between energy and velocity means that tachyons would inhabit a realm of physics completely alien to our everyday experience. While we are accustomed to pushing harder to go faster, tachyons would need to lose energy to accelerate. This counterintuitive behavior is a direct consequence of their imaginary mass and their existence above the speed of light barrier. The mathematical description of tachyons reveals other strange properties. Unlike ordinary particles, which have a minimum energy when they are at rest, tachyons would have a minimum energy when they are moving at infinite speed. This suggests that the natural state of a tachyon is to be moving as fast as possible, with any finite speed representing an excited, higher energy state. Tachyons would also experience space and time differently than ordinary matter. From the perspective of a tachyon, distances would appear contracted and time would flow differently. In fact, depending on their exact speed and direction, tachyons might experience time flowing backward relative to ordinary observers. This temporal reversal is one of the most mind-bending implications of faster-than-light particles. The theoretical framework that allows for tachyons emerges from several areas of advanced physics. In quantum field theory, the mathematical formalism that describes how particles and fields behave at the quantum level, solutions exist that correspond to faster-than-light propagation. These solutions appear naturally when physicists solve the fundamental equations that govern the behavior of matter and energy. String theory, which attempts to describe all fundamental particles as vibrating strings in higher dimensional space, also allows for tachyonic modes under certain conditions. In some versions of string theory, tachyons appear as a sign that the theory is in an unstable state and needs to transition to a more stable configuration. This has led some physicists to view tachyons not as physical particles, but as mathematical indicators of instability in the underlying theoretical framework. Quantum field theory provides another window into the world of tachyons. In this theoretical framework, particles are described as excitations of underlying fields that permeate all of space. When physicists analyze these field equations, they find that certain configurations can propagate faster than light. These superluminal modes share many of the mathematical properties expected of tachyons. The mathematical beauty of tachyon theory lies in its symmetry with ordinary physics. Just as there is an energy barrier that prevents ordinary particles from reaching light speed, there appears to be a corresponding barrier that would prevent tachyons from slowing down to light speed. This creates a kind of parallel universe of particles forever separated from our world by the cosmic speed limit. In some theoretical models, tachyons arise naturally from the mathematical requirement of consistency and symmetry. The equations of physics often have multiple solutions, and while we observe only one class of solutions corresponding to ordinary matter, the mathematics suggests that other classes of solutions, including tachyonic ones, might also be possible. The study of tachyons has also revealed deep connections between seemingly unrelated areas of physics. The mathematics that describes tachyons appears in quantum mechanics, relativity theory, field theory, and even in the study of black holes and cosmology. This suggests that tachyons, whether real or not, represent something fundamental about the mathematical structure of our universe. One of the most intriguing aspects of tachyon theory is how it challenges our understanding of causality and information transfer. If tachyons could carry information, they might allow for communication that travels backward in time from the perspective of certain observers. This possibility has led to intense debate about whether tachyons could exist without creating logical paradoxes. The mathematical treatment of tachyons also reveals that they would interact with ordinary matter and fields in unusual ways. While ordinary particles couple to electromagnetic fields in well-understood ways, tachyons would couple differently, potentially making them extremely difficult to detect with conventional instruments designed to study normal matter. Some theoretical models suggest that tachyons might not interact electromagnetically at all, making them essentially invisible to light-based detection methods. they might interact only through gravitational forces or through entirely new types of fields that we have not yet discovered. This could explain why, despite decades of searching, no tachyons have been directly observed. The theoretical prediction of tachyons represents one of the most striking examples of how mathematics can lead physics into uncharted territory. The equations that successfully describe the known universe seem to point toward possibilities that extend far beyond our current experience. Whether tachyons actually exist remains an open question, but their theoretical possibility continues to inspire physicists to probe the boundaries of our understanding. As we delve deeper into the mathematical foundations of physics, we find that the universe may be far stranger and more wonderful than we ever imagined. The theoretical possibility of tachyons reminds us that the cosmic speed limit, while absolute for ordinary matter, might not represent the final word on what is possible in our universe. The exploration of tachyons has also led to fascinating insights into the nature of symmetry in physics. Throughout the history of science, symmetry has proven to be one of the most powerful guiding principles for understanding the universe. The laws of physics exhibit remarkable symmetries, from the conservation of energy and momentum to the deeper symmetries that govern the fundamental forces. Tachyon theory suggests a profound symmetry in the structure of space-time itself. If ordinary particles are forever confined below the speed of light, and tachyons are forever confined above it, then the speed of light represents a kind of barrier that divides the universe into two distinct realms. This division creates a mirror-like symmetry in the mathematical description of particles and their properties. This symmetry extends to the way tachyons would experience acceleration and deceleration. Just as ordinary particles require infinite energy to reach the speed of light from below, tachyons would require infinite energy to slow down to the speed of light from above. This creates a beautiful mathematical balance where the speed of light serves as an unreachable boundary for both types of particles. The quantum mechanical description of tachyons reveals even more intriguing possibilities. In quantum mechanics, particles can exist in superposition states, where they simultaneously possess multiple properties until measured. A quantum tachyon might exist in a superposition of different velocities, all faster than light, until an interaction forces it to collapse into a specific state. The wave function that describes a quantum tachyon would have properties unlike anything we observe in ordinary matter. While the wave functions of normal particles decrease in amplitude as they extend over large distances, tachyon wave functions might behave in the opposite manner, potentially growing stronger as they propagate through space. This could lead to effects that amplify over cosmic distances. Quantum field theory provides a sophisticated framework for understanding how tachyons might emerge from the fundamental structure of space-time. In this theory, empty space is not truly empty, but filled with quantum fields that fluctuate even in their lowest energy states. These quantum fluctuations could, under certain conditions, give rise to tachyonic excitations that propagate faster than light. The concept of virtual particles in quantum field theory also provides insight into tachyonic behavior. Virtual particles are temporary fluctuations in quantum fields that appear and disappear so quickly that they cannot be directly observed. Some theoretical calculations suggest that certain virtual particles might have tachyonic properties, existing for brief moments above the speed of light before disappearing back into the quantum vacuum. The mathematics of tachyons also appears in the study of phase transitions in condensed matter physics. When materials undergo certain types of phase transitions, the mathematical description sometimes includes tachyonic modes that indicate the instability of the original phase. These tachyonic signatures serve as mathematical harbingers of change, pointing toward new stable configurations. In the realm of particle physics, the search for tachyons has led to investigations of exotic states of matter that might exist under extreme conditions. High-energy cosmic ray interactions, the cores of neutron stars, and the environments near black holes all represent regimes where the normal rules of physics are pushed to their limits. These extreme environments might provide the conditions necessary for tachyonic phenomena to manifest. The theoretical study of tachyons has also influenced our understanding of information and computation. If tachyons could exist and be controlled, they might enable forms of computation that operate faster than light, potentially solving certain mathematical problems in ways that are impossible with ordinary matter. This has led to speculation about tachyonic computers that could perform calculations by exploiting faster than light propagation. The relationship between tachyons and antimatter provides another fascinating avenue of exploration. Antimatter particles have the same mass as their matter counterparts, but opposite charges and other quantum properties. Some theoretical models suggest that tachyons might have their own antimatter counterparts, antitachyons, with properties that mirror ordinary tachyons in complex ways. The mathematical framework describing tachyons also connects to advanced concepts in geometry and topology. The space-time paths that tachyons would follow, called world lines, would have geometrical properties, unlike those of ordinary particles. These exotic world lines might trace out patterns in space-time that reveal new aspects of the universe's geometric structure. String theory, which attempts to unify all forces and particles under a single theoretical framework, provides particularly rich insights into tachyonic phenomena. In certain string theory models, tachyons appear as fundamental modes of vibrating strings. The presence of these tachyonic modes often signals that the theory is in an unstable configuration and must evolve toward a more stable state. This connection between tachyons and instability in string theory has led to important insights about the evolution of the universe itself. Some cosmological models suggest that the early universe might have contained tachyonic fields that drove rapid expansion during the inflationary epoch. As these tachyonic fields decayed into stable configurations, they might have deposited the energy that became ordinary matter and radiation. The study of tachyons has also revealed deep connections to the mathematical concept of analyticity, which deals with functions that can be extended into the complex number plane. The mathematical functions that describe tachyonic particles often require complex analysis techniques that probe beyond the realm of real numbers into abstract mathematical spaces. Advanced mathematical techniques like Wick rotation, which involves rotating the time coordinate into an imaginary direction, have proven useful for studying tachyonic systems. These mathematical tools allow physicists to explore regimes of space-time that are inaccessible to ordinary particles, revealing hidden aspects of the theoretical landscape. The theoretical investigation of tachyons has also led to new ways of thinking about the measurement process in quantum mechanics. If tachyons could exist, how would we detect them? What kinds of interactions would be necessary to observe their properties? These questions have pushed physicists to develop new theoretical frameworks for understanding how faster than light particles might interact with ordinary matter and measuring devices. Some theoretical models suggest that tachyons might be detectable only through their gravitational effects, since gravity is the one force that affects all forms of energy and matter. A tachyon moving through space would create gravitational waves that propagate at the speed of light, even though the tachyon itself moves faster. These gravitational signatures might provide the only way to detect the passage of tachyonic particles. The possibility of tachyonic dark matter has also captured the imagination of theoretical physicists. Dark matter, which makes up most of the matter in the universe, but does not interact electromagnetically, remains one of the greatest mysteries in cosmology. Some speculative models suggest that dark matter might consist partially of tachyonic particles that interact only gravitationally with ordinary matter. The mathematical beauty of tachyon theory extends to its connections with other exotic theoretical constructs. Magnetic monopoles, cosmic strings, and domain walls are all theoretical objects that emerge from advanced physics models. Tachyons share with these exotic objects the property of being mathematically allowed by our theories, but never observed in nature. The study of tachyons has also influenced the development of new mathematical techniques in theoretical physics. The need to handle imaginary masses and faster-than-light propagation has led to new methods in complex analysis, differential geometry, and algebraic topology. These mathematical innovations often find applications in other areas of physics and mathematics. As our theoretical understanding of tachyons continues to evolve, new possibilities and questions continue to emerge. The mathematical framework that describes these faster-than-light particles remains an active area of research, with new insights being discovered regularly. Each new development adds another piece to the puzzle of whether tachyons might actually exist in our universe. The mathematics of tachyons opens doorways to realms of physics that challenge our most basic assumptions about space, time, and causality. These faster-than-light particles exist, for now, only in the realm of theory, but they represent a profound possibility that continues to captivate physicists and expand our understanding of what might be possible in the vast cosmos that surrounds us. The possibility of particles traveling faster than light opens doorways to consequences so profound and mind-bending that they challenge the very foundations of our understanding of reality. If tachyons truly exist, they would not merely represent a curiosity in the realm of theoretical physics, but would fundamentally alter our comprehension of time, space, causality, and the nature of existence itself. The most startling implication of faster-than-light travel involves the nature of time itself. According to Einstein's theory of relativity, time is not a fixed, universal constant, flowing at the same rate for all observers. Instead, time is relative, flowing differently for observers moving at different speeds. This relativity of time becomes especially pronounced as velocities approach the speed of light, and it leads to extraordinary consequences when velocities exceed light speed. For particles moving faster than light, the mathematical framework of relativity suggests something that seems impossible. These particles would experience time flowing backward relative to certain observers. This temporal reversal is not merely a mathematical curiosity, but a fundamental consequence of the geometry of space-time when velocities exceed the cosmic speed limit. To understand this remarkable effect, imagine two observers moving relative to each other at high speed. If a tachyon travels between these observers, one observer might see the tachyon arrive before it was sent, while the other observer sees it arrive after it was sent. The order of events becomes dependent on the motion of the observer, leading to situations where cause and effect can appear reversed. This reversal of temporal order leads to one of the most famous paradoxes associated with faster-than-light travel, the grandfather paradox. If information or matter could travel faster than light, it might be possible to send a message to the past. In the extreme version of this paradox, a person could theoretically travel back in time and prevent their own grandfather from meeting their grandmother, thereby preventing their own birth and creating a logical contradiction. The grandfather paradox illustrates a deeper problem with faster-than-light travel. It seems to violate the principle of causality, the fundamental idea that causes must precede their effects. In a universe where information can travel faster than light, the clear distinction between cause and effect becomes blurred, potentially leading to logical paradoxes that seem to make the universe inconsistent. However, the relationship between faster-than-light travel and causality is more subtle than it first appears. Some theoretical approaches suggest that the universe might have built-in mechanisms that prevent paradoxes from occurring, even if faster-than-light particles exist. These mechanisms might involve quantum effects, thermodynamic constraints, or fundamental limitations on how information can be transmitted. One proposed resolution to the causality problem involves the concept of closed time-like curves, paths through space-time that loop back to their own past. While these curves might exist mathematically, quantum mechanics might prevent them from carrying information in ways that would create paradoxes. The uncertainty principle and other quantum effects might act as cosmic sensors, preventing the universe from becoming logically inconsistent. The implications of faster-than-light travel extend beyond temporal paradoxes to the very nature of simultaneity. In our everyday experience, we have an intuitive sense that events either happen at the same time or in a specific order. However, relativity teaches us that simultaneity is relative, depending on the motion of the observer. For faster-than-light particles, this relativity of simultaneity becomes even more extreme. If tachyons exist and can carry information, they might enable forms of communication that seem to violate our intuitive understanding of time. A message sent via tachyon from Earth to a distant star might arrive before it was sent, from the perspective of certain observers. This could lead to conversations where replies arrive before questions are asked, creating a temporal confusion that challenges our basic understanding of communication and causality. The possibility of faster-than-light communication also raises profound questions about free will and determinism. If information from the future could influence the past, it might suggest that the future is already determined, undermining our sense of free choice and personal agency. Alternatively, it might imply that multiple timelines or parallel realities exist simultaneously, each branching from different possible outcomes. The study of faster-than-light travel has also revealed deep connections to the nature of information itself. In modern physics, information is recognized as a fundamental quantity, as important as energy or momentum. The speed of light represents the maximum rate at which information can be transmitted through space, according to our current understanding. Faster-than-light particles would violate this fundamental limit, potentially allowing for instantaneous communication across arbitrary distances. This possibility of instantaneous communication would revolutionize our understanding of physics and technology. Currently, communication with spacecraft near other planets involves delays of minutes to hours as radio signals travel at light speed. Communication with interstellar space probes would involve delays of years or decades. Faster-than-light communication could eliminate these delays entirely, enabling real-time control of distant spacecraft and instantaneous communication with other civilizations. The implications for space exploration would be profound. Current mission planning must account for communication delays that make real-time control impossible over interplanetary distances. Spacecraft must be designed with autonomous systems capable of making decisions without ground control input. Faster-than-light communication could change this paradigm entirely, allowing for real-time exploration of the solar system and beyond. The possibility of faster-than-light travel also challenges our understanding of energy and momentum conservation. In relativity, energy and momentum are intimately connected to the geometry of spacetime. For particles moving faster than light, these relationships become complex and potentially problematic. The energy required to create or accelerate tachyons might involve exotic forms of matter or energy that we do not currently understand. Some theoretical models suggest that faster-than-light travel might require negative energy or negative mass, exotic forms of matter that have never been observed but are not necessarily forbidden by the laws of physics. These exotic matter states might exist in microscopic quantities in the quantum vacuum, or might be created under extreme conditions in particle accelerators or cosmic ray interactions. The study of faster-than-light travel has also influenced our understanding of the structure of spacetime itself. If particles can move faster than light, it suggests that spacetime might have a more complex structure than we currently understand. There might be hidden dimensions, alternative geometric structures, or exotic topological features that allow for superluminal motion under certain conditions. Some advanced theories in physics, such as string theory and loop quantum gravity, suggest that space-time might not be continuous at the smallest scales, but might have a discrete granular structure. In such theories, the prohibition against faster-than-light travel might apply only to the smooth, continuous space-time that emerges at large scales. At microscopic scales, the discrete structure of space-time might allow for shortcuts or alternative pathways that enable superluminal motion. The possibility of faster-than-light travel also raises questions about the nature of observation and measurement in quantum mechanics. The process of measurement plays a fundamental role in quantum theory, causing wave functions to collapse and determining the outcome of quantum experiments. If faster-than-light particles exist, they might enable new types of measurements that probe quantum systems in previously impossible ways. The relationship between faster-than-light travel and quantum entanglement represents another fascinating area of investigation. Quantum entanglement allows for correlations between distant particles that seem to operate instantaneously, regardless of the distance separating the particles. While these correlations cannot be used to transmit information faster than light, they suggest that the universe contains connections that transcend the limitations of light speed. Some theoretical approaches suggest that tachyons might be related to the mechanism that underlies quantum entanglement. If entangled particles are connected by faster-than-light correlations, tachyons might represent the physical manifestation of these connections. This could provide a deeper understanding of both quantum entanglement and faster-than-light phenomena. The implications of faster-than-light travel extend to cosmology and our understanding of the universe as a whole. The cosmic microwave background radiation provides a snapshot of the universe when it was only 380,000 years old. If faster-than-light particles existed at that time, they might have left signatures in this ancient radiation that could be detected by sensitive instruments. The study of cosmic inflation, the rapid expansion of space that occurred in the early moments after the Big Bang, also involves superluminal phenomena. During inflation, space itself expanded faster than light, carrying matter and energy along with it. While this does not violate relativity because it involves the expansion of space rather than motion through space, it demonstrates that superluminal phenomena can play important roles in cosmology. The possibility of faster-than-light particles also influences our understanding of dark matter and dark energy, the mysterious components that make up most of the universe. Some speculative models suggest that dark matter might consist partially of tachyonic particles that interact only weakly with ordinary matter. Such particles would be nearly impossible to detect directly, but might influence the evolution of cosmic structures in observable ways. As we contemplate these profound implications of faster-than-light travel, we are reminded that the universe may contain phenomena that transcend our current understanding. The possibility of tachyons challenges us to think beyond the limitations of our everyday experience and to consider realities that might seem impossible but could nevertheless be fundamental aspects of the cosmos in which we live. The question of whether tachyons could actually exist in our universe represents one of the most intriguing puzzles in modern physics. While the mathematical framework of relativity and quantum mechanics seems to allow for their existence, the reality of detecting and proving the existence of faster-than-light particles presents challenges that push the boundaries of experimental science and theoretical understanding. The search for tachyons faces a fundamental obstacle that distinguishes it from the hunt for other exotic particles. Unlike ordinary particles, which interact with electromagnetic fields and can be detected through their effects on light, electric fields and magnetic fields, tachyons might not interact electromagnetically at all. This potential invisibility to electromagnetic radiation makes them extraordinarily difficult to detect using conventional particle detection methods. Traditional particle detectors work by observing the electromagnetic interactions of particles as they pass through detection media. When a charged particle travels through a detector, it ionizes atoms along its path, creating a trail of electrical signals that can be measured and analyzed. However, if tachyons do not carry electric charge or interact with electromagnetic fields, they would pass through even the most sensitive detectors without leaving any trace. This electromagnetic invisibility means that tachyons might be streaming through our laboratories, our planet, and our bodies at every moment without our knowledge. They could be as abundant as photons or as rare as the most exotic particles, and we might never know because our primary detection methods rely on electromagnetic interactions that tachyons might not participate in. Despite these detection challenges, several experimental approaches have been proposed and attempted over the decades. Some physicists have searched for tachyons by looking for particles that arrive at detectors before light signals sent simultaneously from the same source. These experiments involve precise timing measurements that push the limits of current technology, searching for arrival time anomalies that might indicate faster than light propagation. High-energy cosmic ray experiments have provided another avenue for tachyon searches. Cosmic rays are extremely energetic particles that arrive at Earth from deep space, carrying energies far beyond what can be achieved in terrestrial particle accelerators. When these cosmic ray particles collide with atoms in Earth's atmosphere, they create cascades of secondary particles that rain down toward the surface. Some researchers have analyzed these cosmic ray showers looking for anomalies that might indicate the production of tachyonic particles. The most sensitive searches for tachyons have focused on neutrino experiments, since neutrinos are the most weakly interacting particles we know and already challenge our detection capabilities. Some experiments have reported anomalous results that could potentially be interpreted as evidence for faster than light neutrino propagation. However, these results have generally been explained by systematic errors or previously unknown effects rather than genuine tachyonic behavior. One of the most famous potential tachyon detections occurred in 2011, when the OPERA experiment in Italy reported that neutrinos seemed to arrive at their detector slightly earlier than expected, based on light speed calculations. The scientific community was understandably excited, but also deeply skeptical, given the extraordinary nature of the claim. After months of careful analysis, the anomaly was traced to a loose fiber optic cable in the timing system, reminding us how difficult it is to make precise measurements at the limits of experimental capability. The challenge of detecting tachyons is compounded by theoretical uncertainties about their properties and interactions. Even if tachyons exist, we do not know what mass they might have, how they might be produced, or what forces might affect them. This uncertainty makes it difficult to design experiments specifically optimized for tachyon detection, since we do not know exactly what we should be looking for. Some theoretical models suggest that tachyons might interact only through gravitational forces, since gravity affects all forms of energy and matter according to general relativity. However, gravitational interactions are extraordinarily weak compared to electromagnetic forces, making gravitational detection of individual particles essentially impossible with current technology. We can detect gravitational waves from massive cosmic events like black hole mergers, but detecting the gravitational signature of individual tachyons would require sensitivity improvements of many orders of magnitude. Alternative detection strategies have focused on the indirect effects that tachyons might produce if they exist in large numbers or high energies. If tachyons interact with ordinary matter through previously unknown forces, they might produce detectable secondary effects, even if the tachyons themselves cannot be observed directly. These secondary effects might include unusual particle decays, anomalous energy distributions, or violations of conservation laws that would signal the presence of faster-than-light particles. The search for tachyons has also motivated the development of new theoretical frameworks for understanding particle interactions. Some physicists have proposed that tachyons might interact through exotic fields that couple to properties other than electric charge or mass. These hypothetical fields might mediate forces that we have not yet discovered, opening up entirely new avenues for tachyon detection and study. Advances in quantum field theory have provided new insights into the possible existence of tachyons. In some quantum field theories, tachyonic modes appear as mathematical solutions that indicate instabilities in the underlying field configuration. However, these theoretical tachyons typically represent unstable states that decay rapidly into stable configurations rather than persistent particles that could be detected experimentally. The relationship between theoretical tachyons and potentially observable, faster-than-light particles remains unclear. The mathematical tachyons that appear in quantum field theory calculations might represent fundamentally different phenomena from the hypothetical particles that could travel through space faster than light. This distinction complicates the interpretation of theoretical predictions and their relevance to experimental searches. String theory has provided another perspective on tachyon existence, suggesting that tachyonic modes might appear in certain string configurations, but would typically signal the need for the theory to evolve towards a more stable state. In this context, tachyons represent transitional phenomena rather than stable particles, making their detection even more challenging since they might exist only briefly during phase transitions or symmetry-breaking events. The possibility of tachyonic dark matter has opened up new avenues for indirect detection. Dark matter makes up most of the matter in the universe, but interacts only weakly with ordinary matter, making it extremely difficult to detect directly. If some fraction of dark matter consists of tachyonic particles, their gravitational effects might be observable through their influence on galaxy formation, cosmic microwave background radiation, or large-scale structure evolution. Recent advances in precision measurement technology have enabled new approaches to tachyon searches. Atomic clocks with extraordinary precision, laser interferometry systems capable of detecting tiny changes in space and time, and superconducting quantum interference devices that can measure minute magnetic field variations all provide new tools for probing the universe at unprecedented sensitivity levels. The development of quantum technologies has also opened up new possibilities for tachyon detection. Quantum sensors that exploit entanglement and superposition effects can achieve measurement sensitivities that exceed classical limits. These quantum-enhanced detection systems might be capable of detecting tachyonic effects that would be invisible to conventional instruments. Machine learning and artificial intelligence techniques are increasingly being applied to particle physics data analysis, offering new ways to search for subtle signals that might indicate tachyon interactions. These computational approaches can analyze vast datasets looking for patterns and anomalies that human researchers might miss, potentially uncovering evidence for exotic particles in existing experimental data. The search for tachyons has also been influenced by developments in cosmology and astrophysics. Observations of distant supernovae, gamma-ray bursts, and other high-energy cosmic events provide natural laboratories for testing whether faster-than-light particles might be produced under extreme conditions. If tachyons are created in stellar explosions or black hole accretion events, they might arrive at Earth before the light from these events, providing a potential signature for faster-than-light propagation. The continued absence of clear tachyon detections has led some physicists to propose that fundamental physical principles might prevent their existence, even if they are mathematically allowed by our current theories. These principles might involve deep connections between causality, quantum mechanics, and thermodynamics that we do not yet fully understand. Alternative theoretical approaches suggest that tachyons might exist, but be confined to microscopic scales or extremely short time intervals, making them undetectable with current experimental techniques. Such particles might play important roles in fundamental physical processes while remaining invisible to direct observation, similar to virtual particles in quantum field theory. The question of tachyon existence continues to drive innovation in both theoretical physics and experimental technique. Whether or not tachyons ultimately prove to exist, the search for them has expanded our understanding of the fundamental limits of physics and pushed the boundaries of what we can measure and observe in the universe around us. In the strange and wonderful realm of quantum mechanics, where particles exist in multiple states simultaneously, and reality itself seems to depend on the act of observation, the possibility of tachyons takes on new dimensions of mystery and complexity. The quantum world operates according to principles that often defy our everyday intuition, and when these principles are applied to faster-than-light particles, the results challenge our understanding of reality in profound and unexpected ways. Quantum mechanics tells us that particles do not have definite properties until they are measured. Instead, they exist in superposition states, where they simultaneously possess all possible values of measurable quantities like position, momentum, and energy. The act of measurement causes this superposition to collapse, forcing the particle to assume specific values. For tachyons existing in the quantum realm, this fundamental uncertainty takes on extraordinary implications. A quantum tachyon would exist in a superposition of velocities, all of which exceed the speed of light. Unlike ordinary particles, which might have a superposition of velocities ranging from 0 to just below light speed, a tachyon's velocity superposition would span the range from just above light speed to potentially infinite velocity. This creates a quantum state unlike anything we observe in the ordinary world. The wave function that describes a quantum tachyon would have properties that challenge our understanding of how quantum systems behave. While ordinary particle wave functions typically spread out and decrease in amplitude as they propagate through space, tachyon wave functions might behave in counterintuitive ways. The mathematics suggests that, under certain conditions, tachyon wave functions could grow stronger as they propagate, potentially leading to amplification effects that have no analog in ordinary quantum mechanics. This potential for amplification raises fascinating questions about the stability of quantum systems containing tachyons. In normal quantum mechanics, the probability of finding a particle somewhere in space must always add up to 1, ensuring that the particle exists somewhere. For tachyons, maintaining this probability conservation while allowing for faster-than-light propagation requires careful mathematical treatment that pushes the boundaries of quantum field theory. The uncertainty principle, which states that certain pairs of properties cannot be measured simultaneously with perfect precision, takes on new meaning when applied to tachyons. For ordinary particles, there is a fundamental trade-off between knowing position and momentum precisely. For tachyons, the uncertainty principle might involve trade-offs between different combinations of properties, potentially allowing for types of quantum uncertainty that do not exist for slower-than-light particles. Quantum entanglement, one of the most mysterious phenomena in quantum mechanics, provides another lens through which to examine tachyonic behavior. When particles become entangled, measurements performed on one particle instantaneously affect the quantum state of its partner, regardless of the distance separating them. This instantaneous correlation seems to violate the speed of light limit, though it cannot be used to transmit information faster than light. Some theoretical approaches suggest that quantum entanglement might be mediated by tachyonic processes that operate behind the scenes of ordinary quantum mechanics. If the correlations between entangled particles are carried by faster-than-light interactions, tachyons might represent the physical mechanism that underlies this most mysterious aspect of quantum theory. This connection could provide a deeper understanding of both entanglement and faster-than-light phenomena. The process of quantum measurement becomes even more complex when tachyons are involved. In ordinary quantum mechanics, measurement causes wave function collapse and determines the outcome of quantum experiments. If tachyons can propagate information faster than light, they might enable types of quantum measurements that probe systems in ways that are impossible with ordinary particles. These exotic measurement processes could reveal new aspects of quantum reality, or might be forbidden by fundamental principles that we do not yet understand. Virtual particles, which appear and disappear in the quantum vacuum on timescales so short that they cannot be directly observed, represent another area where tachyonic effects might manifest. The quantum vacuum is not empty, but filled with fluctuations that continuously create and destroy virtual particle pairs. Some theoretical calculations suggest that under certain conditions, these virtual fluctuations might include tachyonic modes that exist briefly above the speed of light before disappearing back into the vacuum. These virtual tachyons would not violate causality because they exist for such short times and cannot be directly observed or used to transmit information. However, their presence might influence the properties of the quantum vacuum in subtle ways that could be detected through precision measurements of fundamental constants or the behavior of particles in empty space. The concept of quantum tunneling, where particles can pass through energy barriers that would be impossible to cross, according to classical physics, provides another connection to tachyonic phenomena. In quantum tunneling, particles seem to travel faster than light while passing through the barrier region, though the overall process still respects relativistic constraints. Some interpretations suggest that the particles become temporarily tachyonic while tunneling, existing briefly in a faster-than-light state before returning to normal propagation. This tunneling perspective on tachyonic behavior suggests that particles might naturally transition between slower-than-light and faster-than-light states under certain quantum mechanical conditions. Rather than being permanently confined to one side or the other of the light-speed barrier, particles might be able to quantum tunnel between these regimes, spending most of their time as ordinary particles, but occasionally becoming tachyonic during tunneling events. The many worlds interpretation of quantum mechanics, which suggests that all possible outcomes of quantum measurements occur simultaneously in parallel universes, provides yet another framework for understanding tachyonic phenomena. In this interpretation, tachyons might exist in some parallel worlds, but not others, creating a multiverse where faster-than-light particles are possible in certain branches of reality, while remaining absent in others. This multiverse perspective on tachyons suggests that the question of their existence might not have a simple yes or no answer. Instead, tachyons might exist in some versions of reality while being absent in others, with quantum measurements determining which branch of the multiverse we experience. This could explain why tachyons remain undetected despite being mathematically allowed by our theories. The quantum field theory description of tachyons reveals deep connections between faster-than-light propagation and the structure of space-time itself. In quantum field theory, particles are described as excitations of underlying fields that permeate all of space. These fields can support different types of excitations, including potentially tachyonic modes that propagate faster than light. The mathematical treatment of quantum fields allows for solutions that describe faster than light propagation, but these solutions often come with unusual properties that challenge our understanding of causality and information transfer. Tachyonic field excitations might carry energy and momentum in ways that differ fundamentally from ordinary particles, potentially leading to new types of quantum phenomena. Quantum chromodynamics, the theory that describes the strong nuclear force binding quarks together inside protons and neutrons, provides another context where tachyonic effects might appear. Under extreme conditions of temperature and density, such as those that existed in the early universe, or might exist in the cores of neutron stars, the strong force might exhibit phase transitions that involve tachyonic modes. These tachyonic modes would not represent stable particles, but rather instabilities that drive the system toward new equilibrium configurations. The study of these phase transitions has provided insights into both the nature of the strong force and the general properties of quantum systems that undergo rapid changes in their fundamental structure. The quantum mechanical treatment of time itself becomes problematic when tachyons are involved. In ordinary quantum mechanics, time serves as a parameter that describes the evolution of quantum systems. However, if tachyons can influence the past or create closed time-like curves, the usual treatment of time in quantum mechanics might need to be modified or replaced with more sophisticated approaches. Some theoretical frameworks attempt to address this problem by treating time as a quantum mechanical observable, similar to position or momentum. In these approaches, quantum systems can exist in superpositions of different times, potentially resolving some of the paradoxes associated with faster-than-light propagation. However, these theories remain highly speculative and face numerous conceptual and mathematical challenges. The relationship between quantum mechanics and general relativity, Einstein's theory of gravity, becomes even more complex when tachyons are considered. Quantum field theory in curved spacetime, which attempts to combine quantum mechanics with gravitational effects, must grapple with the possibility that faster-than-light particles might create or interact with gravitational fields in unexpected ways. Tachyons moving through curved spacetime might follow geodesics that differ from those of ordinary particles, potentially creating new types of gravitational phenomena. The energy-momentum tensor that describes how matter and energy curve spacetime would need to be modified to account for tachyonic contributions, possibly leading to exotic forms of gravity that we have not yet observed. The search for a unified theory of quantum gravity, which would merge quantum mechanics and general relativity into a single coherent framework, might be influenced by the possibility of tachyonic phenomena. Some approaches to quantum gravity, such as loop quantum gravity and causal dynamical triangulation, attempt to construct spacetime from discrete quantum building blocks. In these theories, the prohibition against faster-than-light travel might emerge naturally from the quantum structure of spacetime itself. Alternatively, these quantum theories of spacetime might allow for tachyonic phenomena under certain conditions, perhaps during phase transitions between different geometrical configurations or in regions where the classical notion of spacetime breaks down entirely. The exploration of these possibilities continues to drive research at the intersection of quantum mechanics, relativity, and geometry. As we delve deeper into the quantum mechanical aspects of tachyonic phenomena, we find that the boundary between the possible and impossible becomes increasingly blurred. The quantum world operates according to principles that often seem to contradict our everyday experience, and when these principles are extended to faster-than-light particles, they open up realms of possibility that challenge our most fundamental assumptions about the nature of reality itself. The relationship between tachyons and the fundamental structure of spacetime represents one of the most profound and complex areas of theoretical physics. If faster-than-light particles exist, they would not merely move through spacetime as passive travelers, but would actively influence and potentially reshape the very fabric of reality itself. The theoretical models that explore these possibilities reveal a universe far stranger and more malleable than our everyday experience suggests. Einstein's general theory of relativity tells us that spacetime is not a fixed stage upon which cosmic drama unfolds, but rather a dynamic participant in the physics of the universe. Matter and energy curve spacetime, while the curvature of spacetime determines how matter and energy move. This intimate relationship between matter and geometry becomes even more complex when we consider the possibility of particles that move faster than light. Tachyons would carry energy and momentum in ways that differ fundamentally from ordinary particles. According to the mathematics of relativity, the energy-momentum tensor that describes how matter affects spacetime would need to include tachyonic contributions that could create entirely new types of gravitational phenomena. These faster-than-light particles might curve space-time in ways that violate our usual understanding of how gravity works. The world lines that tachyons would trace through space-time have geometrical properties unlike those of any known particles. While ordinary particles follow time-like world lines that always point toward the future, tachyons would follow space-like world lines that extend primarily through space rather than time. These exotic trajectories might create regions of space-time with unusual causal properties, where the normal ordering of events breaks down. Some theoretical models suggest that tachyons could create closed, time-like curves, paths through space-time that loop back to their own past. These curves would represent genuine time travel trajectories, allowing information or even material objects to journey backward in time. While the mathematics of general relativity permits such curves under certain conditions, their physical realizability remains hotly debated among physicists. The possibility of closed time-like curves raises fundamental questions about the consistency of physics. If the past can be influenced by the future, it might be possible to create grandfather paradox situations, where events prevent their own causes. Some physicists argue that quantum mechanics or thermodynamic principles might prevent such paradoxes from occurring, while others suggest that the universe might naturally evolve to avoid configurations that would permit time travel. Wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe, represent another area where tachyonic phenomena might play a crucial role. The exotic matter required to keep wormholes open and traversable might need to have tachyonic properties, with negative energy densities and faster-than-light characteristics that violate the energy conditions normally required for stable space-time geometries. If tachyons exist and can be controlled, they might provide the key to creating artificial wormholes that could enable faster-than-light travel through space, rather than requiring faster-than-light motion through space. A spacecraft entering one end of a tachyon-stabilized wormhole could emerge at a distant location almost instantaneously, effectively achieving superluminal travel without violating local speed limits. The study of black holes provides another context where tachyonic effects might manifest in space-time geometry. Near the event horizon of a black hole, space-time becomes so severely curved that unusual phenomena become possible. Some theoretical models suggest that tachyonic modes might naturally arise in the intense gravitational field surrounding black holes, potentially providing new mechanisms for energy extraction or information transfer. Hawking radiation, the theoretical prediction that black holes emit particles and gradually evaporate, might include tachyonic components under certain conditions. These faster-than-light particles could carry information away from black holes in ways that differ from ordinary Hawking radiation, potentially resolving some of the paradoxes associated with black hole information loss. The connection between tachyons and higher dimensional theories of spacetime opens up additional possibilities for exotic phenomena. String theory and other advanced theoretical frameworks often require additional spatial dimensions beyond the familiar 3 dimensions of everyday experience. In these higher dimensional spaces, tachyons might be able to take shortcuts through the extra dimensions, appearing to travel faster than light in our 3-dimensional world, while respecting speed limits in the full higher dimensional space-time. Kaluza-Klein theories, which attempt to unify gravity with other fundamental forces by invoking extra spatial dimensions, might naturally accommodate tachyonic phenomena. Particles moving through these extra dimensions could appear as tachyons when projected onto our familiar 3-dimensional space, providing a mechanism for faster-than-light motion that does not violate the fundamental structure of spacetime. The concept of spacetime foam, proposed by physicist John Wheeler, suggests that at the smallest scales, spacetime itself might have a turbulent, fluctuating structure filled with virtual wormholes and topological fluctuations. In this quantum foam, tachyonic virtual particles might constantly appear and disappear, creating a substrate of faster-than-light activity that underlies the apparently smooth spacetime we observe at macroscopic scales. These quantum fluctuations of spacetime might allow for transient violations of the speed of light limit that do not persist long enough to create paradoxes or violate causality. Just as virtual particles can briefly violate energy conservation through the uncertainty principle, virtual tachyons might briefly violate the speed limit while remaining consistent with the overall structure of physics. Theoretical models of cosmic inflation, the rapid expansion of space that occurred in the early moments after the Big Bang, involve phenomena that are superluminal in nature. During inflation, space itself expanded faster than light, carrying matter and energy along with it. Some models suggest that tachyonic fields might have driven this inflationary expansion, with faster-than-light scalar fields rolling down energy potential hills and driving the exponential growth of space. These inflationary tachyon models provide a concrete example of how faster-than-light phenomena might play crucial roles in cosmology without violating causality or creating paradoxes. The tachyonic fields responsible for inflation would not carry information faster than light, but would instead drive the expansion of space itself, creating the large-scale structure we observe in the modern universe. The study of domain walls, cosmic strings, and other topological defects in spacetime has revealed additional contexts where tachyonic phenomena might arise. These exotic structures, which might have formed during phase transitions in the early universe, could support tachyonic modes that propagate along their surfaces or through their interiors. Such defects might serve as natural laboratories for studying faster-than-light physics under conditions that cannot be replicated in terrestrial experiments. Brain-world models, which suggest that our universe might be a three-dimensional surface embedded in a higher dimensional space, provide another framework for understanding tachyonic phenomena. Particles confined to the brain would normally be limited by the speed of light, but interactions with the higher dimensional bulk space might allow for apparent faster-than-light motion through mechanisms that involve shortcuts through the extra dimensions. The mathematics of supersymmetry, a theoretical framework that relates particles with different spin properties, naturally includes tachyonic modes under certain conditions. When supersymmetry is broken, either spontaneously or explicitly, tachyonic fields often appear as intermediate states in the transition from the supersymmetric phase to the broken phase. These tachyonic modes typically signal instabilities that drive the system toward a new equilibrium configuration. Advanced mathematical techniques from differential geometry and algebraic topology have been applied to the study of tachyonic spacetimes. The global structure of spacetime, containing faster-than-light particles, might have unusual topological properties that affect the causal relationships between events. These topological considerations could provide new insights into whether tachyonic spacetimes are mathematically consistent and physically realizable. The relationship between tachyons and the arrow of time represents another profound area of investigation. Our universe exhibits a clear distinction between past and future, with entropy increasing over time and memories pointing toward the past rather than the future. If tachyons can influence the past or create closed time-like curves, they might disrupt this temporal asymmetry and create regions where the arrow of time becomes ambiguous or even reversed. Some theoretical approaches suggest that the second law of thermodynamics, which describes the increase of entropy over time, might prevent tachyonic time travel, even if it is mathematically allowed by the equations of general relativity. The universe might naturally evolve in ways that preserve causality and maintain the arrow of time, even in the presence of faster-than-light particles. The study of tachyonic spacetimes has also revealed connections to advanced concepts in mathematical physics, including twistor theory, spinor methods, and complex manifold techniques. These sophisticated mathematical tools provide new ways of analyzing the geometric and topological properties of spacetimes that might contain faster-than-light particles. Quantum gravity theories, which attempt to describe the behavior of spacetime at the smallest scales, where quantum effects become important, might naturally accommodate or forbid tachyonic phenomena depending on their specific mathematical structure. Loop quantum gravity, causal dynamical triangulation, and other approaches to quantum spacetime each make different predictions about whether faster-than-light propagation is possible in the quantum realm. As our theoretical understanding of spacetime continues to evolve, the possibility of tachyonic phenomena remains one of the most challenging and intriguing frontiers in physics. Whether tachyons ultimately prove to exist or remain forever in the realm of mathematical possibility, their study continues to reveal new aspects of the deep structure of space, time, and reality itself. The theoretical models that explore tachyons and spacetime push the boundaries of our mathematical and conceptual frameworks, challenging us to think beyond the limitations of everyday experience and consider possibilities that might seem impossible but could nevertheless represent fundamental aspects of the universe in which we live. In the vast landscape of theoretical physics, few concepts capture the imagination quite like the multiverse. The idea that our universe might be just one of countless parallel realities existing simultaneously in an infinite cosmic tapestry. When we combine this mind-expanding possibility with the theoretical existence of tachyons, we enter a realm where faster-than-light particles might serve as bridges between different universes, opening doorways to realities beyond our wildest dreams. The multiverse concept emerges naturally from several areas of modern physics, each suggesting different mechanisms by which multiple universes might coexist. Quantum mechanics, with its emphasis on parallel possibilities and superposition states, provides one pathway to understanding how reality might branch into countless alternative versions. Cosmic inflation theory suggests another route, where different regions of space might evolve into separate universe bubbles, each with its own physical laws and constants. In the quantum mechanical interpretation of the multiverse, every quantum measurement causes reality to branch into multiple parallel worlds, each corresponding to a different possible outcome. In some branches, particles behave one way, while in others, they behave differently. This branching process creates an ever-expanding tree of parallel realities, where every possible history unfolds simultaneously in different branches of the multiverse. Tachyons could play a remarkable role in this quantum multiverse by potentially providing a mechanism for communication or travel between different branches of reality. If faster-than-light particles can influence the past or create closed time-like curves, they might be able to reach backward through the branching structure of the multiverse, connecting different quantum histories that would otherwise remain forever separated. Imagine a tachyon originating in one branch of the quantum multiverse, traveling faster than light through space-time, and arriving in a different branch where quantum measurements had different outcomes. Such a particle could carry information about alternative realities, potentially allowing observers in one universe to learn about the parallel worlds that exist alongside their own reality. The eternal inflation model of cosmology provides another framework where tachyons might connect different universes. In this model, space is constantly expanding and creating new regions that evolve into separate universe bubbles. Each bubble might have different values of fundamental constants, different particles, and different physical laws. The space between these bubbles continues to inflate, carrying them apart at speeds faster than light. However, if tachyons exist and can travel faster than the expansion of space itself, they might be able to journey between these cosmic bubbles, serving as messengers that carry information from one universe to another. A tachyon created in our universe bubble could potentially travel through the inflating space between bubbles and arrive in a completely different universe with entirely different physics. These inter-universe tachyons would face extraordinary challenges as they transit between cosmic domains with different physical laws. A tachyon that behaves in a particular way in our universe might transform or decay when it encounters regions of space where the fundamental constants have different values. The very definition of faster than light might change as the tachyon moves between regions with different speed of light limits. String theory provides yet another perspective on the multiverse and its potential connection to tachyonic phenomena. In string theory, the fundamental building blocks of reality are tiny, vibrating strings existing in multiple dimensions. The different ways these strings can vibrate correspond to different particles and forces. The theory predicts an enormous number of possible configurations, each corresponding to a different universe with unique physical properties. This string theory landscape contains an estimated 10 to the 500th power different possible universes, each representing a different way that the extra dimensions of string theory can be configured. Tachyons appear naturally in many of these configurations, often as signals of instability that drive the system from one configuration to another. In this context, tachyons might serve as guides that help universes evolve through the landscape of possibilities. The anthropic principle, which suggests that the properties of our universe are fine-tuned to allow for the existence of intelligent observers, takes on new meaning when combined with tachyonic multiverse theories. If tachyons can carry information between different universes, observers in one universe might be able to influence the development of life and consciousness in parallel realities. This could create a kind of cosmic natural selection, where universes that develop intelligent life capable of manipulating tachyons gain advantages in the multiverse ecosystem. Such universes might be able to steer their own evolution or even create new universe bubbles with properties optimized for life and consciousness. The possibility of tachyonic communication between parallel universes raises profound questions about identity and free will. If every possible decision branches reality into multiple parallel worlds, and tachyons can carry information between these branches, then our choices might influence not only our own future, but the futures of countless parallel versions of ourselves. Consider the implications of receiving a tachyonic message from a parallel universe where you made different life decisions. Such information could fundamentally alter your understanding of yourself and your place in the cosmic order. The knowledge that infinite versions of yourself exist in parallel realities, some more successful or happy than others, might change how you view your own experiences and choices. The technology required to detect or generate tachyonic signals between parallel universes would represent the ultimate achievement in physics and engineering. Such devices would need to be sensitive enough to detect particles that might interact only weakly with matter in our universe, while also being capable of distinguishing between tachyons originating from our own reality and those arriving from parallel worlds. The development of inter-universe communication technology could revolutionize our understanding of science and philosophy. Access to information from parallel universes, where different experiments were performed or different theories were developed, could accelerate scientific progress by allowing researchers to learn from the discoveries made in alternative realities. The ethical implications of tachyonic multiverse communication are staggering. If we could send messages to parallel universes, what responsibility would we have to warn other versions of humanity about potential disasters or to share beneficial technologies? The ability to influence parallel realities might come with cosmic responsibilities that dwarf any ethical considerations we currently face. The concept of quantum immortality, which suggests that consciousness might persist by continuously branching into universes where survival is possible, becomes even more complex when tachyonic communication is considered. If faster than light particles can carry information between branches of reality, they might enable forms of consciousness transfer or backup that could preserve awareness across multiple parallel existences. Some speculative theories suggest that consciousness itself might have tachyonic properties, explaining phenomena like intuition, creativity, and the hard problem of consciousness through faster than light information processing that operates across multiple parallel realities simultaneously. In this view, Our minds might naturally access information from parallel universes through tachyonic processes that we do not yet understand. The relationship between tachyons and the wave function collapse in quantum mechanics might provide another mechanism for multiverse interaction. If the collapse of quantum wave functions involves faster than light information transfer, as some interpretations suggest, then tachyons might play a fundamental role in determining how reality branches and which outcomes become manifest in our observed universe. The study of quantum entanglement across parallel universes represents another frontier where tachyonic phenomena might prove crucial. If particles can become entangled with their parallel universe counterparts, tachyons might mediate these correlations, creating a vast network of quantum connections that spans the entire multiverse and enables instantaneous information sharing across all possible realities. The possibility that our universe might be part of a vast computational simulation running on some cosmic computer becomes even more intriguing when tachyonic multiverse theories are considered. If multiple simulated universes can communicate through faster-than-light channels, the entities running these simulations might use tachyonic networks to coordinate between different computational processes or to merge information from multiple parallel simulations. Dark matter and dark energy, which make up most of our universe but remain mysterious, might have connections to tachyonic multiverse phenomena. If dark matter consists partially of particles that interact primarily with parallel universe versions of ordinary matter, or if dark energy represents the influence of parallel universe expansion on our own space-time, then tachyons might provide the mechanism that enables these cross-universe interactions. The ultimate fate of our universe, whether it will expand forever, collapse in a big crunch, or transition to a new phase of existence, might be influenced by tachyonic connections to parallel realities. Information or energy flowing in from other universes through faster-than-light channels could alter the evolution of our cosmos in ways that we cannot predict based solely on observations within our own reality. As we contemplate these extraordinary possibilities, we are reminded that the universe, or rather the multiverse, might be far stranger and more interconnected than we have ever imagined. Tachyons, if they exist, might not merely be exotic particles that violate our understanding of space and time, but could represent the very mechanism by which infinite parallel realities remain connected in a vast cosmic web of faster-than-light communication and interaction. The exploration of tachyonic multiverse theories pushes the boundaries of both science and imagination, challenging us to consider possibilities that transcend the limitations of our single universe perspective, and to contemplate our place in an infinite cosmos where every possibility exists somewhere in the vast tapestry of parallel realities. The quest to detect tachyons represents one of the most challenging and sophisticated endeavors in experimental physics, pushing the boundaries of measurement technology and theoretical understanding to their absolute limits. While these hypothetical faster-than-light particles remain elusive, the search for evidence of their existence has driven remarkable innovations in detection methods, data analysis techniques, and our fundamental understanding of what it means to observe phenomena that might exist beyond the conventional limits of space and time. Modern particle physics relies on massive, incredibly sophisticated detection systems that can identify and track individual subatomic particles as they race through elaborate experimental apparatus. The Large Hadron Collider at CERN, stretching 27 kilometers in circumference beneath the border between France and Switzerland, represents the pinnacle of current particle detection technology. Its detectors can identify particles that exist for mere fractions of a second and track their paths with extraordinary precision. However, detecting tachyons would require entirely new approaches to particle physics experimentation. Traditional detectors work by observing the electromagnetic interactions of charged particles as they pass through detection media. When a charged particle travels through a detector, it ionizes atoms along its path, creating cascades of secondary particles and electrical signals that can be measured and analyzed. But if tachyons do not interact electromagnetically, they would pass through even the most sophisticated detectors without leaving any trace. This fundamental challenge has led physicists to develop innovative indirect detection strategies that look for the secondary effects that tachyons might produce, rather than trying to observe the particles themselves directly. These approaches focus on searching for violations of energy and momentum conservation, anomalous timing relationships, or other signatures that might indicate the presence of faster-than-light particles in high-energy interactions. Cosmic ray experiments provide one of the most promising avenues for tachyon detection. Cosmic rays are extremely energetic particles that arrive at Earth from deep space, carrying energies that far exceed anything achievable in terrestrial particle accelerators. When these cosmic ray particles collide with atoms in Earth's atmosphere, they create extensive air showers containing billions of secondary particles that cascade down toward the surface. The Pierre Auger Observatory in Argentina and the Telescope Array in Utah represent state-of-the-art cosmic ray detection facilities that monitor vast areas of the Earth's surface for these particle showers. These experiments can detect individual cosmic ray events with energies exceeding 10 to the 20th power electron volts, energies so extreme that they approach the theoretical limits of particle acceleration in the universe. If tachyons are produced in these ultra-high energy cosmic ray interactions, they might arrive at ground-based detectors before the light and slower particles from the same air shower. This temporal anomaly could provide a clear signature of faster-than-light propagation, assuming that tachyons interact weakly enough with matter to reach the ground but strongly enough to produce detectable signals in specialized instruments. Neutrino experiments offer another window into potential tachyonic phenomena. Neutrinos are the most weakly interacting particles in the standard model of particle physics, able to pass through entire planets with only a tiny probability of interaction. This makes them extremely difficult to detect, but it also makes them ideal probes for studying fundamental physics under extreme conditions. The IceCube Neutrino Observatory at the South Pole uses a cubic kilometer of Antarctic ice as a detection medium. Instrumented with thousands of sensitive photodetectors that can identify the faint flashes of light produced when neutrinos occasionally interact with ice nuclei. Similar experiments like Super Kamiokande in Japan and Antares in the Mediterranean Sea use different detection media, but employ the same basic principle of watching for the rare interactions of these elusive particles. These neutrino detectors are sensitive enough to potentially identify tachyonic neutrinos or other faster-than-light particles if they interact through similar weak force mechanisms. The precise timing capabilities of modern neutrino detectors could potentially identify particles that arrive earlier than expected based on light speed calculations, providing evidence for superluminal propagation. Gravitational wave detectors represent another frontier in the search for tachyonic phenomena. The Laser Interferometer, Gravitational Wave Observatory, known as LIGO, and its European counterpart Virgo, have revolutionized astronomy by directly detecting ripples in space-time caused by colliding black holes and neutron stars. These instruments can measure changes in distance smaller than 1/10,000th the width of a proton, making them among the most sensitive measurement devices ever constructed. If tachyons interact gravitationally with ordinary matter, they might produce gravitational wave signatures that differ from those created by conventional matter and energy. Tachyonic gravitational waves might propagate at the speed of light, even though their sources move faster than light, creating timing relationships and wave patterns that could reveal the presence of superluminal matter. Advanced atomic clocks and precision timing experiments provide yet another approach to tachyon detection. Modern optical atomic clocks can keep time with precision approaching 1 part in 10 to the 18th power, making them sensitive to tiny variations in the flow of time that might be caused by tachyonic influences. Networks of synchronized atomic clocks around the world could potentially detect temporal anomalies that might indicate faster than light information transfer. The Global Positioning System, which relies on precise timing signals from orbital satellites, already provides a worldwide network of precision clocks that could be monitored for tachyonic effects. Any systematic deviations in GPS timing that cannot be explained by known physics might hint at the influence of faster-than-light particles on the propagation of electromagnetic signals. Quantum interference experiments offer another avenue for tachyon searches. These experiments exploit the wave nature of quantum particles to create interference patterns that are exquisitely sensitive to tiny changes in physical conditions. If tachyons can influence quantum systems, they might alter interference patterns in ways that could be detected with current technology. The development of quantum sensors that exploit entanglement and superposition effects has opened up new possibilities for detecting exotic phenomena. These quantum-enhanced measurement devices can achieve sensitivities that exceed the limits imposed by classical physics, potentially making them capable of detecting tachyonic effects that would be invisible to conventional instruments. Machine learning and artificial intelligence techniques are increasingly being applied to the analysis of experimental data from particle physics experiments. These computational approaches can identify subtle patterns and correlations in vast data sets that human researchers might miss. Advanced algorithms trained to recognize the signatures of new physics might be able to identify evidence for tachyonic phenomena buried in the data from existing experiments. The search for tachyons has also motivated the development of new theoretical frameworks for understanding what constitutes evidence for exotic phenomena. Traditional particle physics relies on the detection of resonances, peaks in energy spectra that correspond to the creation and decay of new particles. However, tachyons might not produce conventional resonances, requiring new statistical methods and analysis techniques to identify their presence. Some researchers have proposed using astrophysical observations as natural tachyon detectors. Gamma-ray bursts, supernovae, and other high-energy cosmic events release enormous amounts of energy in brief periods, potentially creating conditions where tachyonic particles might be produced. If tachyons are created in these events and travel faster than light, they might arrive at Earth before the electromagnetic radiation from the same events. The Fermi Gamma Ray Space Telescope and other space-based observatories continuously monitor the sky for these high-energy events, providing precise timing information that could reveal faster-than-light propagation. Any systematic early arrival of high-energy particles compared to lower-energy photons from the same source might indicate the presence of tachyonic phenomena. Dark matter detection experiments, which search for the mysterious particles that make up most of the matter in the universe, might also be sensitive to tachyonic dark matter if such particles exist. These experiments use underground laboratories shielded from cosmic rays and employ ultra-sensitive detectors cooled to temperatures near absolute zero. If tachyonic particles make up part of the dark matter component of the universe, they might occasionally interact with the detection media used in these experiments. The signatures of tachyonic dark matter interactions might differ from those of conventional dark matter candidates, requiring new analysis techniques and detection strategies. The search for evidence of extra dimensions, which are predicted by string theory and other advanced theoretical frameworks, might also reveal tachyonic phenomena. If tachyons can take shortcuts through higher dimensional space, experiments designed to probe extra dimensions might indirectly detect their presence through missing energy or anomalous particle trajectories. Large particle accelerators like the Large Hadron Collider create conditions of extreme energy density that might be conducive to tachyon production. While these experiments are not specifically designed to search for faster-than-light particles, their enormous datasets and sophisticated analysis techniques make them capable of detecting unexpected phenomena that might hint at new physics. The development of room-temperature quantum computing and quantum communication networks might provide new tools for tachyon detection. If tachyons can influence quantum systems, or if quantum effects can enhance sensitivity to exotic phenomena, then quantum technologies might open up entirely new approaches to searching for faster-than-light particles. As our experimental capabilities continue to advance and our theoretical understanding deepens, the search for tachyons remains an active and evolving field. Whether these elusive particles ultimately prove to exist or remain forever in the realm of theoretical possibility, the quest to detect them continues to drive innovation in experimental physics and expand our understanding of the fundamental limits of measurement and observation in the universe around us. The search for evidence of tachyons represents more than just the hunt for exotic particles. It embodies humanity's relentless drive to push beyond the boundaries of the known and to explore the deepest mysteries of existence itself. In this quest, we are reminded that the universe may hold secrets that challenge our most basic assumptions about reality, and that the next great discovery might be waiting just beyond the limits of our current understanding. The mere possibility of tachyons existing in our universe forces us to confront some of the most profound philosophical questions that have puzzled humanity for millennia. These hypothetical, faster-than-light particles do not merely challenge our scientific understanding of space and time. They strike at the very heart of our concepts of reality, causality, free will, and the nature of existence itself. To contemplate tachyons is to embark on a philosophical journey that reaches into the deepest mysteries of consciousness and meaning. The concept of time has been central to human philosophical thought since the earliest recorded history. We experience time as a flowing river, carrying us inexorably from past through present toward future. Our memories point backward, our hopes point forward, and our consciousness seems anchored in the fleeting present moment. This subjective experience of temporal flow forms the foundation of our understanding of causality, where causes precede effects in an orderly sequence that gives structure and meaning to existence. Tachyons threaten to shatter this comfortable understanding of temporal order. If particles can travel faster than light and potentially influence the past, the clear distinction between cause and effect becomes blurred. Events might precede their own causes, creating loops of causality that seem to violate the logical structure of reality itself. This possibility forces us to question whether our intuitive understanding of time reflects a fundamental aspect of the universe or merely the limitations of our human perspective. The philosophical implications of reversed causality extend far beyond abstract theoretical concerns. If effects can precede causes, what does this mean for moral responsibility? Can we be held accountable for actions whose consequences might somehow influence their own origins? The possibility of temporal loops challenges the very foundation of ethics and moral philosophy, which traditionally assumes that agents act freely and bear responsibility for the future consequences of their choices. Consider the profound philosophical puzzle of receiving information from the future through tachyonic communication. If tomorrow's events could somehow send messages to today, would those messages represent genuine knowledge of a predetermined future? Or would they merely describe one possible timeline among many? The reception of future information might itself alter the course of events, creating paradoxes that seem to make the concept of a fixed future logically impossible. This possibility leads to deep questions about the nature of free will and determinism. Our sense of personal agency depends on the belief that our choices matter, that we can influence the future through our decisions and actions. But if information from the future can reach the present, it might suggest that future events are already determined, undermining our sense of genuine choice and reducing human action to the playing out of a predetermined script. Alternatively, tachyonic time travel might support theories of multiple parallel realities, where each possible choice creates a branching timeline. In such a multiverse, free will might be preserved because every possible decision occurs in some parallel reality, while tachyonic messages arrive from futures that represent only one possible path among infinite alternatives. This perspective preserves human agency, but at the cost of making our individual choices less meaningful in the grand scheme of existence. The philosophical tradition has long grappled with questions about the nature of identity and personal continuity over time. What makes you the same person today that you were yesterday? Philosophers have proposed various theories, from psychological continuity based on memory and personality to physical continuity based on bodily identity. The possibility of tachyonic time travel adds new complexity to these questions by potentially allowing interactions between different temporal versions of the same person. If tachyonic communication could enable conversations between past and future selves, what would this mean for personal identity? Would receiving advice from your future self represent a form of guidance? Or would it constitute an external influence that undermines the authenticity of your own development? The possibility of temporal self-interaction challenges our understanding of individual autonomy and the nature of personal growth and learning. The concept of knowledge itself takes on new dimensions when confronted with tachyonic possibilities. Traditionally, knowledge has been understood as justified true belief about reality, typically acquired through observation, reasoning, and experience. But what kind of knowledge would be represented by information received from the future? Would such information count as genuine knowledge? Or would it represent something categorically different that transcends our normal epistemological frameworks? The possibility of faster-than-light particles also challenges our understanding of the relationship between mind and reality. Human consciousness seems intimately connected to the flow of time, with awareness moving from moment to moment, in synchrony with the progression of physical events. If tachyons can transcend temporal boundaries, they might suggest the existence of aspects of reality that operate outside the temporal framework that constrains human consciousness. Some philosophers and scientists have speculated that consciousness itself might have tachyonic properties, allowing minds to access information from across space and time in ways that transcend the limitations of physical signal transmission. This possibility could provide new perspectives on phenomena like intuition, creativity, and the mysterious hard problem of consciousness, which concerns how subjective experience arises from objective physical processes. The relationship between tachyons and the nature of truth presents another profound philosophical challenge. Truth has traditionally been understood as correspondence between statements and reality, or as coherence among beliefs and experiences. But if tachyonic phenomena can create causal loops where events influence their own preconditions, the very concept of objective truth might need to be reconsidered. In a universe where faster-than-light particles can create temporal paradoxes, truth might become contextual or observer dependent in ways that go beyond the relativity already established by Einstein's theories. Different observers might experience different versions of reality depending on their relationship to tachyonic causal loops, making the search for universal truth even more complex and challenging. The philosophical implications of tachyons extend to questions about the nature of possibility and necessity. Our understanding of what is possible is typically constrained by the laws of physics as we currently understand them. The speed of light has represented an absolute boundary, dividing the possible from the impossible. If tachyons exist, they would expand the realm of possibility in ways that might require us to reconsider fundamental philosophical categories. The ancient philosophical distinction between being and becoming takes on new significance in the context of tachyonic physics. Traditional metaphysics has often debated whether reality consists of static being or dynamic becoming, whether the universe is a fixed four-dimensional block or an evolving process of emergence and change. Tachyons might provide new perspectives on this eternal philosophical debate by suggesting mechanisms through which becoming might transcend the normal constraints of temporal order. The question of meaning and purpose in human existence becomes more complex when considered in light of tachyonic possibilities. If faster-than-light particles can connect different moments in time, or even different parallel realities, the significance of individual human lives might need to be understood in a broader context that transcends our normal temporal boundaries. Our actions might have consequences that extend far beyond what we can currently imagine or comprehend. The possibility of communication with parallel universes through tachyonic channels raises profound questions about moral obligations and cosmic citizenship. If our choices can influence parallel versions of ourselves and others across multiple realities, the scope of ethical consideration might need to expand to encompass infinite alternative worlds. This could either make moral action more meaningful by extending its impact across multiple realities, or more overwhelming by making the consequences of every choice infinitely complex. The relationship between tachyons and human spirituality presents another rich area for philosophical exploration. Many spiritual traditions have long claimed that reality extends beyond the physical world accessible to our senses, involving transcendent dimensions of existence that operate according to different principles. Tachyonic phenomena might provide a physical framework for understanding how such transcendent realities could interact with the ordinary world. The possibility that consciousness might persist or communicate across temporal boundaries through tachyonic mechanisms could provide new perspectives on questions about life after death, the continuity of personal identity beyond physical existence, and the relationship between individual consciousness and cosmic consciousness. These considerations bridge the gap between scientific speculation and spiritual inquiry in ways that enrich both domains. As we contemplate these profound philosophical implications of tachyonic possibilities, we are reminded that science and philosophy are deeply interconnected endeavors that illuminate different aspects of the mystery of existence. The theoretical possibility of faster-than-light particles challenges us to think beyond the boundaries of conventional understanding and to consider realities that might transcend the limitations of our current perspective. Whether tachyons ultimately prove to exist or remain forever in the realm of theoretical speculation, their contemplation expands our philosophical horizons and deepens our appreciation for the profound mysteries that surround us. In exploring the implications of these hypothetical particles, we engage with questions that have puzzled humanity throughout history, while opening new avenues for understanding the nature of reality, consciousness, and our place in the cosmic order. The philosophical journey into tachyonic possibilities reminds us that the universe might be far stranger and more wonderful than we can currently imagine, filled with mysteries that challenge our deepest assumptions about the nature of existence itself. In this ongoing exploration, we discover not only new ways of understanding the cosmos, but also new perspectives on what it means to be conscious beings, seeking truth and meaning in an infinite and mysterious universe. As we stand on the threshold of a new era in scientific discovery, the theoretical possibility of tachyons continues to inspire researchers, engineers, and visionaries to push the boundaries of what we consider possible. While these faster-than-light particles remain elusive, the pursuit of understanding them has already begun to transform our approach to fundamental physics, space exploration, and our conception of humanity's future among the stars. The coming decades may witness breakthroughs that either confirm the existence of tachyons or definitively rule them out, but either outcome will profoundly impact the trajectory of human knowledge and cosmic exploration. The future of tachyon research lies at the intersection of advancing theoretical understanding and increasingly sophisticated experimental capabilities. Quantum field theory continues to evolve, with new mathematical frameworks and computational techniques providing deeper insights into the fundamental structure of space-time and the particles that might inhabit it. String theory, loop quantum gravity, and other approaches to quantum gravity are beginning to make testable predictions about the behavior of matter and energy under extreme conditions where tachyonic phenomena might manifest. The development of quantum computers represents a revolutionary tool for tachyon research, offering computational power that could solve previously intractable problems in theoretical physics. These quantum machines exploit the same mysterious principles of superposition and entanglement that might govern tachyonic behavior, potentially providing new ways to simulate and understand faster-than-light phenomena. As quantum computers become more powerful and accessible, they may enable theoretical breakthroughs that illuminate the possible existence and properties of tachyons. Machine learning and artificial intelligence are increasingly being integrated into fundamental physics research, offering new approaches to pattern recognition and data analysis that might reveal subtle signatures of exotic phenomena. Advanced neural networks trained on vast datasets from particle accelerators, cosmic ray detectors, and astrophysical observations might identify tachyonic signals that have been hiding in plain sight within existing experimental data. The next generation of particle accelerators promises to reach energy scales that approach the fundamental limits of physics, where new phenomena and particles might emerge. The proposed future circular collider at CERN would dwarf the current Large Hadron Collider, creating collision energies that could potentially produce tachyons if they exist within the reach of terrestrial experiments. These machines will probe energy regimes where the distinction between matter and space-time itself becomes blurred, possibly revealing new physics that includes faster-than-light particles. Cosmic ray experiments are expanding their reach and sensitivity, with new detector arrays covering vast areas of the Earth's surface and new techniques for analyzing the cascades of particles that rain down from space. The planned giant radio array for neutrino detection would use the Moon as a detector, monitoring for radio pulses created when ultra-high energy neutrinos interact with lunar rock. Such experiments might be sensitive enough to detect tachyonic cosmic rays or other faster-than-light particles arriving from the depths of space. Space-based telescopes and observatories offer unprecedented opportunities to search for tachyonic phenomena on cosmic scales. The James Webb Space Telescope and its successors will observe the universe with extraordinary sensitivity across multiple wavelengths of light, potentially detecting the signatures of faster-than-light particles in distant galaxies, stellar explosions, or the cosmic microwave background radiation itself. Gravitational wave astronomy is entering a golden age, with new detectors coming online and existing facilities being upgraded to achieve even greater sensitivity. The planned laser interferometer space antenna will detect gravitational waves from space, free from the seismic noise that limits ground-based detectors. These space-based instruments might be sensitive enough to detect gravitational wave signatures of tachyonic matter, if such signatures differ from those produced by conventional matter and energy. The search for dark matter and dark energy continues to drive the development of ever more sensitive detection technologies. Underground laboratories buried deep within mountains provide unprecedented quiet environments for detecting the faintest interactions between exotic particles and ordinary matter. If tachyons make up part of the dark sector of the universe, these facilities might finally provide the evidence needed to confirm their existence. Advances in precision measurement technology are pushing the limits of what we can observe and quantify in the natural world. Optical atomic clocks now achieve precision levels that were unimaginable just decades ago, making them sensitive to tiny variations in the flow of time that might be caused by tachyonic influences. Networks of these ultra-precise clocks spread across the globe might detect temporal anomalies that indicate faster-than-light information transfer. The development of room-temperature quantum sensing technologies promises to bring quantum-enhanced measurement capabilities out of specialized laboratories and into widespread use. These quantum sensors exploit entanglement and superposition to achieve sensitivity levels that exceed classical limits, potentially making them capable of detecting tachyonic effects that would be invisible to conventional instruments. If tachyons are eventually discovered and their properties understood, the implications for space exploration would be revolutionary. The ability to communicate faster than light would transform how we explore the solar system and beyond. Currently, communication with spacecraft near other planets involves delays of minutes to hours, while communication with interstellar probes would involve delays of years or decades. Tachyonic communication could eliminate these delays entirely, enabling real-time control of distant spacecraft and instantaneous communication with robotic explorers throughout the galaxy. The development of tachyonic communication technology would require advances in several areas of physics and engineering. We would need to understand how to generate, detect, and modulate tachyonic signals, as well as how to build transmitters and receivers that could operate reliably over interstellar distances. The engineering challenges would be immense, but the potential rewards would justify the most ambitious technological development programs in human history. Beyond communication, the possibility of tachyonic propulsion systems captures the imagination of space exploration enthusiasts and theoretical physicists alike. If tachyons can be harnessed to enable faster-than-light travel, either through direct propulsion or through the creation of space-time shortcuts, like wormholes, the entire galaxy could become accessible to human exploration within human lifetimes. The concept of tachyonic space drives remains highly speculative, requiring not only the existence of tachyons, but also the ability to control and manipulate them in ways that we cannot currently imagine. Such technology might involve exotic matter states, negative energy densities, or manipulation of higher dimensional spaces that extend beyond our normal three-dimensional experience. The search for extraterrestrial intelligence might be revolutionized by tachyonic communication technologies. If advanced civilizations have discovered how to communicate faster than light, they might be using tachyonic networks that we cannot currently detect. The development of tachyonic receivers might suddenly reveal a galaxy teeming with intelligent life that has been communicating through channels invisible to our current technology. The possibility of detecting alien tachyonic communications has inspired new approaches to the search for extraterrestrial intelligence. Rather than focusing solely on radio and optical signals that travel at light speed, future searches might monitor for faster-than-light communications that could indicate the presence of technologically advanced civilizations capable of manipulating tachyonic phenomena. The implications of tachyonic technology for human civilization extend far beyond space exploration. If faster-than-light communication becomes possible, it could enable global coordination and cooperation on scales never before achievable. Instantaneous communication across any distance could facilitate international collaboration on challenges like climate change, disease prevention, and resource management, potentially ushering in a new era of human unity and shared purpose. The economic implications of tachyonic technology would be profound, potentially revolutionizing industries that depend on information transfer and communication. Financial markets, scientific collaboration, entertainment, and education could all be transformed by the ability to transmit information instantaneously across any distance. The competitive advantages gained by the First Nations or organizations to develop tachyonic communication could reshape the global balance of power. The philosophical and cultural implications of discovering tachyons would be equally significant. Confirmation that faster-than-light particles exist would represent a fundamental shift in our understanding of reality, potentially opening up new perspectives on the nature of time, causality, and consciousness itself. This knowledge could influence art, literature, religion, and philosophy in ways that we can barely imagine. educational systems would need to evolve to help future generations understand and work with tachyonic technologies. New fields of study combining physics, engineering, and philosophy would emerge to address the complex implications of faster-than-light phenomena. Students would need to develop intuitions about space-time and causality that go beyond our current everyday experience. The international cooperation required to develop and regulate tachyonic technologies would necessitate new forms of global governance and scientific collaboration. Treaties and agreements would be needed to ensure that faster-than-light communication and travel are used for peaceful purposes and the benefit of all humanity rather than becoming sources of conflict or inequality. As we look toward the future of tachyon research, we are reminded that the most profound discoveries in science often come from unexpected directions. Whether tachyons ultimately prove to exist or remain forever in the realm of theoretical possibility, the quest to understand them continues to push the boundaries of human knowledge and imagination. The future may hold discoveries that transform our understanding of the universe in ways we cannot currently anticipate. Advanced civilizations elsewhere in the galaxy might have already mastered tachyonic technologies, waiting for humanity to develop the scientific maturity necessary to join a cosmic community that operates beyond the limitations of light-speed communication and travel. The journey toward understanding tachyons represents more than just the pursuit of exotic physics. It embodies humanity's relentless drive to transcend limitations and explore the deepest mysteries of existence. In this ongoing quest, we may discover not only new aspects of the physical universe, but also new possibilities for human consciousness, creativity, and connection across the vast expanses of space and time. As we continue to probe the boundaries of the possible and explore the frontiers of knowledge, the theoretical possibility of tachyons reminds us that the universe may be far stranger and more wonderful than we currently comprehend. The future of tachyon research and its implications for space exploration represent an open door to possibilities that could transform our species and our understanding of our place in the cosmic order, carrying us toward a future where the speed of light no longer represents the ultimate boundary of human reach and understanding. As our journey through the mysterious realm of tachyons draws to a close, we find ourselves standing at the edge of an infinite ocean of cosmic mystery, gazing out toward horizons that stretch beyond the boundaries of our current understanding. The theoretical possibility of faster-than-light particles has taken us on an extraordinary voyage through the deepest questions of physics, philosophy, and human existence itself. Whether tachyons ultimately prove to be real or remain forever in the realm of mathematical possibility, their contemplation has illuminated the profound depths of mystery that surround us in this vast and wonderful universe. Throughout our exploration, we have seen how the simple question of whether particles can travel faster than light opens doorways to considerations that challenge our most fundamental assumptions about the nature of reality. The speed of light, which has stood for over a century as the ultimate cosmic speed limit, might not represent the final word on what is possible in our universe. The mathematical equations that so successfully describe the behavior of matter and energy seem to whisper of possibilities that extend beyond our everyday experience into realms where time flows backward, where causes follow effects, and where the impossible becomes merely improbable. The search for tachyons reminds us that the universe is far stranger and more wonderful than our ancestors could have imagined. From the quantum realm, where particles exist in multiple states simultaneously, to the cosmic scales where space itself expands faster than light, reality consistently surprises us with phenomena that defy our intuitive understanding. In this context, the possibility of faster-than-light particles represents not an isolated curiosity, but part of a larger pattern of cosmic strangeness that continues to reveal itself as our knowledge deepens. We have seen how tachyons could potentially bridge the gap between different universes in an infinite multiverse, carrying information, and perhaps even consciousness between parallel realities where every possible outcome unfolds simultaneously. This possibility transforms our understanding of identity, choice, and meaning, suggesting that our individual lives might be connected to infinite variations of ourselves across countless alternative realities. The philosophical implications of tachyonic phenomena extend far beyond the realm of physics into the deepest questions of human existence. If faster-than-light particles can influence the past or enable communication across time, they challenge our understanding of free will, moral responsibility, and the nature of consciousness itself. These considerations remind us that science and philosophy are not separate endeavors, but intertwined explorations of the same fundamental mysteries. The quest to detect tachyons has driven remarkable innovations in experimental physics and measurement technology, pushing the boundaries of what we can observe and quantify in the natural world. Whether or not these efforts ultimately succeed in finding evidence for faster-than-light particles, they have expanded our technological capabilities and deepened our understanding of the fundamental limits of observation and measurement. The potential discovery of tachyons would revolutionize space exploration and our relationship with the cosmos, enabling instantaneous communication across galactic distances and perhaps even faster than light travel to distant stars. Such capabilities could unite humanity with hypothetical alien civilizations in a cosmic community that operates beyond the constraints of light speed limitations. Yet even if tachyons prove not to exist, their theoretical possibility has enriched our understanding of the mathematical structures that underlie physical reality. The equations of physics, when explored in their full generality, reveal possibilities that extend far beyond the phenomena we currently observe. This suggests that the universe might contain hidden aspects of reality that await discovery by future generations of explorers and investigators. As we contemplate the vast cosmos above us, filled with billions of galaxies, each containing billions of stars, we are reminded of how much remains unknown and unexplored. The light from distant stars that reaches our eyes tonight began its journey long before our planet existed, carrying information about cosmic events that occurred in the deep past. Yet this light represents only a tiny fraction of the information and phenomena that might be racing through space at this very moment. If tachyons exist, they could be streaming through our bodies and our world right now, carrying messages from distant civilizations, information from parallel universes, or signals from the deep future that we lack the technology to detect. The possibility that such phenomena might surround us unnoticed adds a layer of mystery and wonder to our everyday existence. The story of tachyons also reminds us of the power of human imagination and mathematical reasoning to probe beyond the boundaries of direct experience. The fact that our equations seem to allow for faster-than-light particles demonstrates the remarkable ability of mathematics to reveal aspects of reality that we might never observe directly. This suggests that the universe operates according to deep mathematical principles that extend far beyond the physical phenomena we can currently access. The exploration of tachyonic possibilities has shown us how scientific investigation naturally leads to profound questions about the nature of existence itself. In seeking to understand whether particles can travel faster than light, we have been led to consider the nature of time, causality, consciousness, and meaning in ways that enrich both our scientific knowledge and our philosophical understanding. The collaborative nature of modern tachyon research, involving physicists, mathematicians, engineers, and philosophers from around the world, demonstrates the power of human cooperation in addressing the deepest questions of existence. The international scientific community, working to understand these phenomena, represents humanity at its best, united in the pursuit of knowledge and understanding that transcends national boundaries and cultural differences. As we look toward the future, the possibility of tachyonic discoveries continues to inspire new generations of scientists and thinkers to push the boundaries of knowledge and imagination. Whether through theoretical breakthroughs, experimental discoveries, or technological innovations, the quest to understand faster-than-light phenomena will continue to drive human progress and expand our cosmic perspective. The universe holds countless mysteries that we have yet to uncover, from the nature of dark matter and dark energy to the possibility of extra dimensions and parallel realities. Each discovery reveals new questions and opens new avenues for exploration, ensuring that the frontier of knowledge will continue to expand for generations to come. In the quiet moments when we gaze up at the star-filled sky, we can reflect on our place in this vast cosmic tapestry and wonder what secrets the universe still holds. The possibility of tachyons reminds us that reality might be far richer and more complex than we currently understand, filled with phenomena that could transform our understanding of existence itself. The infinite mysteries that surround us invite us to remain curious, humble, and open to possibilities that might seem impossible from our current perspective. The universe has consistently surprised us with its strangeness and beauty, and it likely holds surprises yet to come that will challenge our understanding and expand our sense of wonder. As we rest beneath the ancient light of distant stars, we can take comfort in knowing that the pursuit of knowledge continues, that brave explorers of mind and cosmos work tirelessly to uncover the secrets of existence, and that the universe itself seems designed to reward those who seek to understand its deepest mysteries. The story of tachyons, whether they prove real or remain theoretical, reminds us that we live in a universe of infinite possibility where the next great discovery might be waiting just beyond the horizon of our current understanding. Rest now beneath the stars, knowing that the mysteries of the cosmos are still waiting to be uncovered, and that each new day brings us closer to understanding the infinite wonders that surround us in this vast and mysterious universe we call home.